Well, good evening. I'm Charles Schultz. It's the 25th of March, 2022, and this is the Randomizer for the 25th of March. And we're going to look at the term coefficient tonight, which has both physics and mathematical meanings. They're not so different from each other, but each of them does have a distinct application. So before we get into coefficients and what they are, I'm going to urge everybody to go to schultzlaboratories.com and universesciencecenter.com and come to our registration page, become a member and support what we're doing, and help us expand and add more galleries and more interactive content to our virtual world. If you are an educator and you have a skill you wish to pass on, get in touch with us and we can help you set up a virtual gallery or classroom to exhibit your works and to share what you know with others. Share your skills before they're lost. That's a big thing. One of the things that holds our civilization together is the sharing of knowledge. So this is your opportunity to do it in a virtual space, and I'd say it's one of the best options going because people all over the world can get involved and interact with it and learn from it. So that being said, randomizers occur every 6 p.m. weekdays, and our lessons are going to resume very shortly at 9 p.m. Mondays only, and we're going to go directly into the robotics class. So it's going to be interesting. We'll cover some of the history of robotics, some of the design features, what you need to build a robot, how to program a robot, and you're going to learn an awful lot from it. It's going to be a great deal of fun. And if you follow along, you can build your own robot using the parts we use. We'll specify everything and show you exactly what to do. And of course, we'll leave it open-ended, so if you want to expand on it later, that can easily be done. And we'll be starting live robotics classes here at Schultz Laboratories in the very near future. We'll post that online as well. We can have up to 10 to 12 students maximum, I think, and we'll get all of that worked out very shortly. So we're looking forward to everybody being able to participate in a live hands-on robotics course with us right here in Northern Florida. So let's get on to coefficients. So many of us had algebra in high school, and basically it's an essential skill. And I know a lot of people who don't use algebra in their everyday lives directly, but just about everything we do is technical in nature and has its roots somewhere in mathematics. And as I often like to say, mathematics is the language of the universe. It really describes everything in physics, everything in reality. And because of that, we become quite adept at making simulated worlds in the computer using mathematics. But a coefficient, what is a coefficient? Well, in a mathematical sense, a coefficient is a value that you multiply by something to scale it to a wanted answer. And one way of thinking of it is this: if you have a certain coefficient and you have a function that produces an answer, you multiply the coefficient by it and it gives you an answer that will match some graph or curve or help you predict an action or a result. And so a coefficient basically is just a number in an equation that is used to multiply by something else. When we get into physics, however, coefficient takes on a slightly different meaning. In physics, everything is pragmatic. It's based on measurements of reality, predictions and models we make, and the ability to create a new model and then test it before we put the first piece of metal or the first rivet or screw or wire in it. Mathematics as a tool is necessary for us to simulate and model things before we waste a lot of money and hardware building something that might not work. So coefficients are an important part of the models, and I'll give you an example. Anybody who works in aeronautics or flight knows of something known as the coefficient of drag. This is sometimes also referred to as the Reynolds number. This is the fluid turbulence and friction associated with movement through a medium, whether it's something that moves in the water or something that moves in the air. And why is it important? And what does it do for us? Well, if you can imagine driving along in a car with the window down and you stick your hand out the window and you can feel the air pressing back against your hand, you know that the stronger that force is, the faster your vehicle must be moving. And conversely, the faster the vehicle moves, you know it's going to push your hand back more firmly. So that figure of drag is the figure of how much stiction there is for the air and the surface of your hand, and all the shape of the geometry. And if you're very adept at designing an aeronautical surface, you'll make a surface that eliminates or reduces the drag greatly so that you can have control over your flight. This drag number does not increase linearly with your speed, but it has a strong knee in it. And so to give an example, if you're driving along in an automobile, the drag goes up pretty uniformly, this coefficient of drag, up to about 40 miles per hour or so, and then it goes up basically as the cube of your speed. It goes up very rapidly. So basically, this is a nonlinear function. So there is an equation you use that generates this coefficient of drag, and then this coefficient is what you multiply by the surface of your aeronautics device or your vehicle or an object, and it gives you a very good prediction of how much resistance it's going to encounter moving through the air. So the coefficient of drag is figured out by an equation, and that number is then multiplied by some factor, such as the area of the thing that's moving. Another one is the coefficient of friction. So what is friction? Friction is a mechanical force, and it has a scale that is proportional to how much force is being applied to move an object against the surface. And the coefficient of friction is often characterized by the Greek letter mu, and so this symbol is often seen as the micro symbol by people who use it in other disciplines. Mu, the coefficient of friction, is controlled by many things. And one of the first things we learn is when you have a lot of jagged surfaces moving over something, and those surfaces drag on each other, how do you eliminate some of the friction? Well, if you could fill the gaps in those surfaces with something, oil, wax, you could reduce the coefficient of friction and make the surface more slippery. So this coefficient is calculated by a number of factors, and one of them is the area of the surface, and you can actually model it by the number of points and the size of the points, the jaggedness of the surface, and you come out with some equations that are pretty good at approximating how much of this friction you're likely to encounter. And then likewise, you can also figure how much of it you can reduce. Now here's an interesting fact. Sometimes friction works in ways we don't understand or predict fully when we're using the traditional models. The foot of the gecko, a type of lizard, can stick on a glass window, which is very, very smooth, but it does it in a very curious manner. There is a force between one surface and another. The atoms in that surface or molecules want to stick together, and it's called van der Waals force. And this force can be increased if you have a huge amount of surface area. So what a gecko's foot does is it has many, many folds with a lot of surface area, and when they stick to a surface, they stick to it in a manner called adhesion, and it literally can displace some of the air molecules so the air pressure itself helps. A suction cup can do that. There are other ways of making this work as well, but we can calculate from the gecko's foot with a different mathematical model how successfully it will stick to a surface, and we now have many types of tape and adhesive based on this principle that can stick to a wall really well, but then if you peel it off gently at the corner, it will come right off and you can reuse it again and again. Traditional adhesive tapes use a chemical bonding method and often are very difficult to get off or will leave gum behind. But the coefficient of friction is used to calculate some of the stiction forces on a surface here. Another one, the coefficient of heat conduction. How do you know when something is a conductor versus an insulator? Well, you can look at how well the material that it is made of allows molecular motion to be transmitted through it. And some materials are excellent conductors of heat. Copper is a very well-known example, and so is aluminum. The fins on any air conditioner use aluminum because it has a very high coefficient of heat transfer. And this means that when I apply some heat to one side, it's going to move right through it very quickly to the other side. This makes aluminum a very powerful tool for conducting heat away from things and creating heat sinks, for example. Heat exchangers also use this principle, the coefficient of heat conduction, to allow heat from a cold object to flow from a hot surface to a cold surface very easily. Heat exchangers are often used to take, let's say, the heated water from a solar collector and heat the water in your home and transfer the energy into it so it goes into your water system, your hot water storage. Why would you do this? Why not simply run your water up to the roof, heat it up, and bring it back in? Well, the answer is in the winter, in many places, that water would freeze and it would burst the heat conducting pipes and your system would be destroyed. So instead, you use two fluids. And the first fluid is the water you're trying to heat for your home usage, and the second fluid is a water containing antifreeze. So what you put into the solar heat collector on your roof is a water with an alcohol or glycol dissolved in it to increase its ability to resist freezing, to lower its freezing point so that it's not likely to rupture the pipe. So then what gathers the heat through aluminum or copper tubing and black painted solar surfaces, gathering surfaces, is that working fluid. The working fluid carries all the heat down to a heat exchanger, and using the proper coefficient of heat transfer, it moves that heat into the water that's going into your hot water storage system. So this is how most of these water heating systems that are based on solar power are made to operate. And in many cases, similar things are done to carry heat away from things that are extremely hot, such as the radiator system in an automobile. So the coefficient of heat transfer is a very important function to know here. And here's another thing to understand. Many times, the coefficient that we're talking about can only be derived by a fairly complicated equation. So you can go online to many interesting resources, such as the government's atmospheric models online. They literally have models of the atmosphere, the pressure at various altitudes, the heat conduction, the drag coefficients. You can look them up on a table, put in a few numbers, they'll give you an answer. So a lot of this is online and very easy to find, and it allows you to do a lot of really interesting experimentation with conditions you don't normally encounter in your home, the conditions at the edge of space, for example. Here's another interesting coefficient that I've used quite often, and it is a coefficient of absorption. Let's say you have something that's radioactive, and you need to provide a level of shielding for it. Now, certain materials are very good at blocking radiation, certain aren't so good. One of the most important factors that emerges is called halving distance, and that's the thickness of a material that it takes to cut the amount of radiation literally in half. And so for gamma radiation, lead has a really good halving distance. And if you go from lead to iron, then it takes about 60% more iron to block it in thickness terms than it would for, let's say, lead, as an example. One of the good things about soil and concrete is they make very good absorbers. And so you'll find that in many cases, if a company has, let's say, a large isotope source that generates radiation for treatment of cancer or tumors, or for treating certain materials, or as a reference standard, and I'll explain that in a moment, they will often have the thing housed in a pit surrounded by plenty of dirt and concrete, and they don't worry so much about the cost of lead shielding then. They'll have a lead shield when they bring the source up for service or for certain operations, and then when they're done with it, they'll drop it back into the ground because soil has a great insulating capacity. Now, it doesn't have a real high blocking distance or absorption distance, but there's so much of it and it's basically free. I mean, if you're standing on the ground, you're standing on dirt. And with a little bit of shoveling and a little bit of care, you can put anything in there and shield it pretty effectively. So in many cases, you'll find that this was one of the things that determined how people would build fallout shelters in times in the past. And many companies would find that soil was also good for blocking other effects. Many of the large steel mills or foundries would often have turbine wheels or flywheels, which they would spin up the speed and store a huge amount of kinetic energy. And how did they prevent a disaster? Well, in some cases they didn't. And there are historical accounts of flywheels breaking free and racing miles downhill into the town and causing disasters. And in most cases, they learned enough to dig a pit, put the flywheel in the pit, and encase it in steel so if a disaster did occur, the physical stresses of having to burn through the steel and the dirt and the concrete would be enough to contain the disaster. I remember we had a high-speed centrifuge used for testing acceleration resistance in microchips. And it basically was something like a dishwasher. It had a large steel lid that would come down and you'd twist the handles and it'd clunk together. And it was basically 3/4-inch steel all around. And then they'd spin it up and they'd test the chips inside. And then you'd see if anything cracked or anything was wrong. In one occasion, one of the counter masses that was used to balance the rotor was omitted. The results were very expensive and very comical. The machine spun up to speed, the quill snapped, and as you can imagine, the rotor was spinning inside this steel tub, running around in here making the most awful noise you can imagine. And this machine is dancing around on its corners, walking away from the wall, about a couple thousand pounds of steel, rips the power cable out, dances around the room, all the while with the flywheel inside spinning down and running down in frequency until finally when it stopped and the horrified operator grabs the lid, clicks it open and opens it, and this billow of smoke comes out, and there's this wreckage of steel and aluminum inside the thing. Anyway, it was quite the thing to see and hear, and I hope never to see that again. But anyway, coefficients. So there are coefficients for friction, for drag, for absorption, for heat conduction, and just about anything you can imagine. And one of the others I didn't mention was reciprocity. That is the coefficient of a recovery. If you have a rubber ball and you compress it, it has a certain amount of reciprocity, this coefficient of recovery, and it determines how readily it will bounce. Strangely, you might think that a rubber ball on a steel surface would probably be one of the bounciest things there is, but in reality, it turns out that a steel ball bearing falling on a steel surface bounces higher and has more recovery than a rubber ball does. How counterintuitive is that? A steel bearing will bounce higher than a rubber ball in the same steel box. So some of the strange things that you learn. And if you calculate it, yeah, the numbers are good for it. So the coefficient works. You just have to pay attention sometimes. So I hope that this has been helpful. You can hear more about this by looking at many of the educational videos that I've seen on YouTube and by going to some of the online researches that you can do with Google. Look up coefficients, look up reciprocity, convection, conduction, and you'll see that every one of these coefficients is a number derived from some function or equation that you then multiply by something to get your wanted result. So you see the difference between a physical coefficient and a mathematical coefficient. Mathematics coefficients are more ethereal, more abstract. The ones in physics about the real world take an application where you can model something, apply the math, and see the real world results. So I hope that this makes it clear and helps you understand some of what we have going on with coefficients. And now I'm going to open the floor up for anybody who has questions or suggestions. And I hope that you're enjoying these randomizers. We're going to have many more with a lot more interesting subjects in coming times. Every weekday, 6 p.m., join us for the randomizer. It's sure to be something interesting. And meanwhile, questions, answers, inputs, very good. I'm going to read my quote for the day now. I love this one. It's one of my favorites. And it simplifies things so much. For all the law is fulfilled in one word, even in this: you shall love your neighbor as yourself. That's Galatians 5:14. Be kind to people. It's an easy thing. It costs us nothing. And it really goes a long way. So I hope that everybody has a wonderful weekend. Enjoy your life. Be good to everybody. And as I always say, make the world a better place. I'm Charles Schultz with the Randomizer, and thank you for watching. Have a great weekend.